Thank you for the nice introduction, and thanks a lot for coming to my talk today. I'm really happy to be here. So as we run some of the most fundamental server applications on today's commonly used hardware types, most of the underlying infrastructure is actually wasted. There is simply a huge gap between what hardware offers to software, like mainly in terms of parallelism, and how much of it can software actually exploit. So in the course of my PhD, I basically tried to bridge this gap for the transaction processing applications in data management. And today, I will mainly talk about these applications, but in the end, I will conclude with more high-level takeaway messages that I think are valid for software systems in general. Now, first of all, what is transaction processing? Well, it was the main reason the relational database model was invented back in the day, and today it's still one of the most crucial applications in data management. Because it mainly deals with how we handle money in banks, in finance sector, so it has a multi-billion-dollar industry for itself. And some characteristics for these applications are that you see many concurrent requests, so many users try to access the database concurrently, and their requests usually touch a few records. For example, in the case of a bank, you usually touch a few accounts in a transaction. And they require really high and predictable performance, especially because they deal with small amount of data and users want fast responses. Now, today we also have many online applications that require transactions, and some of these applications might have less strict transactional semantics than others. For example, you will probably worry less about seeing your Facebook wall update getting lost compared to an update to your bank account getting lost. But the core characteristics of the applications don't really change. And in fact, these online applications, they amplify some of these characteristics, meaning that you have many more users accessing the database concurrently, and therefore you need to operate on big servers in data centers to manage the load. And also accessing a small portion of the data, considering the whole volume of the data, requires you to have smart indexing or caching techniques so that you can still provide high and predictable performance to the users. Now, moving from the application space to the hardware we run these applications on, the server hardware has gone through major advancements over the decades. So before the last decade, hardware mainly innovated on implicit parallelism through techniques like pipelining, instruction level parallelism, or simultaneous multithreading. Now, around 2005, due to power concerns, vendors stopped putting more complexity in one core, and they started putting more cores in one processor, so that we would be still able to turn Moore's law into more performance. And today we increasingly have multiple processors in one machine, so the core-to-core communication latencies are no longer uniform. And finally, in the future, we expect to see even more cores in one processor and more processors in one machine, and we expect them to be heterogeneous in terms of the functionality they provide. So in this picture, basically what hardware has given us over the years is more and more opportunities for parallelism, even though its type and level changed over the years. And for our applications, the crucial thing is that they need to be able to exploit this parallelism because it's highly unlikely to disappear with the emerging hardware. And additional thing is that we increasingly see more non-uniform, more heterogeneous hardware, so our applications should be aware of this heterogeneity, so they should know how to optimally run the task over these numerous heterogeneous cores. So now let's see how traditional transaction processing actually performs on this hardware. So here we are thinking a really simple transaction. So it just looks for one customer in the database and checks the balance. We are running this on an open source storage manager, ShoreMT, and we are using an Intel server. Now, on this graph, on the x-axis, we are increasing the number of worker threads in the system, and the y-axis plots to throughput, the speed up on the throughput over the case of a one worker thread. So what we would like to see ideally is that as we increase the number of worker threads, we can utilize the available cores the same way, and we can achieve linear speed up, and that's what the red line here corresponds. Now, what happens in the real systems is that the state-of-the-art systems, they are not so bad. You can still see straight lines, but the important thing is that the gap between the ideal line you want to see and the conventional line basically increases as you increase the parallelism in the system. And this is not just problematic for today's hardware, but it will be even worse with the emerging hardware. Now, let's also look at what happens like within a core. How can the one thread can actually exploit what is given microarchitecturally from the hardware side. And here we draw the instructions we retire in a cycle on this processor, and we have four-way issue processors here, meaning that in each cycle you can actually retire 4 instructions. So what happens with the conventional systems is that when running transaction processing, they barely retire 1. So there is quite a bit of underutilization at this level as well. So to recap our problems, basically conventional transaction processing failed to exploit what is given from the hardware side in 2 dimensions. One is that they cannot really exploit the multi-core parallelism, and they also underutilize the microarchitectural resources of a single core. So during the next half an hour, I will present some insights and techniques that aims to solve this problem. But now I want to give a more high-level insight that I think is valid across all the techniques we use. Now, in the conventional transaction execution, what we usually do is we consider transactions as one big task. So we basically think of them as black boxes, and we schedule them randomly on one of the available cores in the system. And this eventually leads to suboptimal scheduling decisions or data assignment decisions. So what we will instead do is basically, yeah.
Now by transaction, you mean a database transaction, so like several operations, all of which have to be atomic?
Yeah.
So it's a very complex task.
Yeah. It performs many database operations, many subtasks.
So I may have missed this, but have you said like what database engine we're talking about here, and like how it does locking? Because
So
they don't like Oracle doesn't schedule threads, right?
Right now, yes, but I wanted to mention like how the really traditional, even the really traditional Oracle design was doing things. Of course, we have improved this over the years. For sure, we pay more attention to where we schedule things and so on. And yeah, I will talk about that later. So what we will instead do is to think of transactions composed of different parts, and we will determine these parts based on the data and instructions accessed in each part. And then based on the locality we want to improve, we will, so this can be either for data or instructions, we will assign each of the cores to a specific part of the transaction and basically spread the execution of a transaction over multiple cores. So by doing this, basically if we go back to the previous graphs again, now I also draw the alternative line with green. So we can both improve the scalability of the system and also exploit better what is given in terms of resources from within a core. Now for the rest of the talk, we will first focus on improving scalability at the whole machine level from transaction processing, and we will do that by basically eliminating most problematic critical sections in the system. Then we will see two alternative scheduling techniques that aim to improve the underutilization of processors, and they will basically aim to improve cache locality for the at the right level in the memory hierarchy. So and then we will conclude with more high-level lessons from these works for applications in general, and see what can we do from this point on. Now let's start with the scalability. Traditionally, so this is a picture of a traditional shared everything architecture. It's just a simple sketch of it. So at the higher level, you usually have the management of worker threads in the system that execute transactions. And at the lower level, you have the management of database pages. So these database pages, they can be either the data pages that keep the actual records, and or they can be the index pages that basically allow us fast access to a particular portion of the data. Now, again, traditionally, when you have concurrent requests in the system, these requests will be assigned to one of these worker threads randomly, and here we have the blue and green worker thread. So since these threads, since the data is shared, these threads might access the same data, and they might actually have conflicts over the same data. So to ensure the safety of the database records, at the higher level, we have a centralized lock manager that basically ensures isolation among concurrent transactions. And at the database pages level, we have short-term locks that we acquire whenever we want to access a database page. Now, all these things, they basically clutter the execution of a transaction with many critical sections. And basically, this is the reason that hinders your parallelism on multi-cores. So, for example, if we look deeper and see the critical section breakdown of again, really simple transaction that just looks for a customer and updates the balance, we see that even for this simple transaction, we need to go through around 70 critical sections. Yeah.
What database engine is this?
This here we use SureMT again. Throughout the talk, I will be using the SureMT storage manager.
I'm not really familiar with Short.
Yeah, so it's not commercial. It's mostly used for research, but it has all the traditional storage manager components, like a lock manager, like a.
Benchmark against commercial tools or open source tools? Is it comparable?
So we have a benchmarking layer on top, and it's so we have some publications. So the time it was developed, it was like scalability-wise, it was comparable to the commercial databases of that time. But so but this was like, I would say, around 2005 maybe that we did it the last time. So in
Just to make a comparison
yeah.
though with a commercial database like Oracle,
Mhm.
I don't know the internals of it either, but I
Yeah.
do know that it has optimistic locking, right?
Yeah,
It
yeah.
has this specifically to avoid a lot of these
Yeah, yeah.
lock problems.
So actually, so what we will do here, it's similar to what it will be similar to what Oracle sort of has today. It's not as strict as what we do, but basically you can find similar ideas in many storage managers today.
Okay.
But what I want
If I
to
wanted to compare this to an open source tool, would like Postgres?
yeah,
be a comparison?
Postgres or MySQL, I can ensure you that this would perform better. And so
And then this is a TPCC workload, right?
no, this one is again, I'm using a very simple transaction to indicate, like, even for this you have this, and if you have TPCC, this is gonna be even more. Okay. But like in the very traditional sense, Oracle also look like this, and right now they have, as I said, not exactly the same, but similar techniques to overcome these problems. Not all of them are very specifically documented, so yeah.
Sorry,
Yeah.
so just so I'm clear, this is pessimistic locking,
Yes, yes.
and that is sort of, and the thing he was bringing up is, this had been the standard, but you feel that some commercial things are now changing their locking strategy, so that the worry is that this ratio here is not the actual
Yeah.
ratio and not it.
Yeah, yeah. So, but like the problem they were facing was, again, the problem I presented like 5 minutes ago. So like all that sort of came up from this, and all the commercial systems that aim at improving this, basically, in essence, what they would do is to basically reduce that like unscalable portion of the critical section. You might have like various techniques to do that, but like what I want to show you today is that you need to focus on there, and like not all the critical sections might be your enemy. You need to focus on the right ones. Okay. So yeah, in this picture, as I said, we go through a lot of critical sections, and what's more problematic is that most of these critical sections belong to a type called the unscalable, where as you increase the parallelism in the system, the contention on these critical sections has potential to increase accordingly. The other two types I have shown in lighter colors. For the cooperative critical sections, for example, threads contended for a resource can aggregate their requests and do it all at once later. So as you increase the parallelism in the system for this, you have more opportunity to aggregate work. And for the fixed type of critical sections, basically the contention on these are basically depends on the constant number of threads that are communicating over this critical section. So it's independent of the overall parallelism. So again, in the traditional way of thinking, the problematic thing is that we have unpredictable data accesses, so we need to be pessimistic to protect this data. And that's why we execute a lot of unscalable critical sections, even in simple transactions, and these basically prevent the scalability of our traditional systems on multi-cores.
Is there a correlation between the type of the lock that you're seeing, or the critical section that you're seeing, and the data that you're accessing? So do you see, for example, more unscalable, critical sections on the index data versus the pages?
So
or are just completely randomly distributed?
So rather than associating it with data, we associate it with the data storage manager components. For example, like the critical sections in lock manager, or for the locks that you use to protect pages, like all the threads might access here, so we call it unscalable. Whereas like like the critical sections in logging, like many threads can aggregate their work there and do like batch logging
So
requests.
this categorization comes from just looking at where the logs are.
Yes, yes, rather
and
than the
rather
data.
than,
Yeah,
the-
yeah. So to overcome this problem, we will basically do a redesign in both layers of the system. So at the higher level, what we will basically do is to assign a worker thread to a specific portion of the data. For example, here we assign the blue worker thread to customers whose names start from A to M, and to the rest of the customers we assign the green worker thread. And this way we can basically decentralize the log manager at this level. And going to the database pages, we basically, instead of having a single rooted index structure, we will have a multi-rooted one and map each of the subtrees here to a subtree at the higher levels of the system. And we can also at the databases we can make sure that they are pointed by a single leaf page in the index, and this way we can ensure single threaded accesses to both database records and to database pages. So like in the case of Oracle, actually what they do is they don't have such strict assignments of worker threads, but they basically just partition the some of these lower level structures so that you again reduce the contention to some extent to these regions. So this resulting design, we call it physiological partitioning. And now if you look at the critical section breakdown we have, we eliminated majority of the unscalable critical sections, and what remains is like mostly the lighter types now. Now, how this affects performance? Again, here we again use the Shore Empty Storage Manager with the simple transaction I have been using till now, and like this is a read-only transaction, so ideally it has like no contention. So on the x-axis here, we again increase the number of worker threads executing this transaction, and on the y-axis we report the throughput, which is like transactions executed in a second for us, and here it's plotted in thousands. Yeah.
So, are the number of partitions proportional to the number of worker threads that are planned for? Or
Yes.
so,
Yeah.
so that means you had 16 partitions then for the.
Yeah, for this machine, yeah, 16,
right.
and for the other one it was 64. I would say actually it doesn't have to be, but for these experiments, we the database size is it can fit in memory. So if you have that, it's better to align the number of partitions to the number of hardware contexts you have in the machine. But you can have more. Yeah.
You just mentioned that this is a read-only task.
Mm-hmm.
So if I'm understanding correctly, you're giving the conventional thing the best possible scenario. 'Cause it
Yes,
doesn't have
yes,
to be
that's what
logging.
I'm trying to do. Yeah.
Okay.
So from these graphs, what we see is that like physiologically partitioned system, it both performs better and also scales better compared to the conventional system. And both on the San Niagara machine, which has support for 64 hardware contexts, and on the AMD machine, which has faster processors. And what we also see is that, again, the gap between the conventional line and the PLP design basically increases as we increase the parallelism in the system, and this is what we want to see actually for scalability specifically.
Yeah, this works because I assume I'm just trying to understand. This works well because your input is random in this case, right? You're creating these customers randomly.
Yeah.
So if there was instead, if you were, had queries which look at a certain section of the data, right? Multiple transactions coming to a certain part. How does it compare?
Um,
And can you do this split dynamically, or in this case you're doing it dynamic or statically?
So we also have the dynamic portion of it actually. So we sort of have histograms that look at things at the sub-partition level. So you observe how hot a particular portion of the data is, and you can adjust your partitions so it doesn't have to be equal. Yeah.
Aren't these transactions modeled after TPCC?
The design or the
The actual transactions, how you pick customers, basically, etc.
Yeah. I mean, it is. So in the case of TPCC, you basically have a lot more work in one transaction. So here, it was again a simple transaction to give
Right, But my point is that if they are modeled after TPCC, then it's not uniform random. The actual probability is skewed.
Yeah. I would say for TPCC, it's again not so skewed, but like for workloads like TPCE, especially, you have that, and again, like for that we have like in the background basically repartitioner thread that observes things and that sees how we can repartition.
It seems that if you're basically visiting rows with kind of uniform random patterns, right, so they're equally popular,
Yeah.
you're actually probably underreporting the benefit you have, right? So if you have some sort of zip mismatch, you can expect a lot more contention for a small set of rows, and there your effect is stronger.
Yes. I mean, for if you have an transaction that updates data, that's the case. But sometimes with read-only transactions, with read-only transactions, actually you can have some caching effects that actually benefits the conventional system. But yeah, that goes both ways. You can also have contention if you have. Okay. Any more questions regarding this part? We have looked how we can improve things at the whole machine level, and our main methodology here was to basically analyze the critical sections we have and eliminate the ones that are the real danger to scalability of the system. Now let's look at the main sources of underutilization at the microarchitectural level and what can we do about them. So let's first remind ourselves what is the typical memory hierarchy of the common server hardware today. So we usually see three levels of caches, and like closest to core we have split L1 instruction and data caches, and we usually have a private L2 cache per core again, and there is also a shared L3 or last level cache. Then we have the main memory, which today can actually keep the working set size for most of the transaction processing applications. And in this hierarchy, of course, as you go down here, you observe more and more latencies. I'm giving the numbers I give is from more for the current Intel processors. Now, in practice, what happens is that usually, like reaching L1, it's no penalty if you can find an item there because of the out of order execution. But as you go down, you might observe possible stall time because you are waiting for the item to do your execution and to move forward. So let's first see like how much of these stalls we actually have for the transaction processing systems. And here, this time I'm using some of the standardized transaction processing benchmarks, TPCC and TPCE. TPCC models a brokerage hours, and TPC is more like a warehouse management thing. And TPC stands for Transaction Processing and Performance Console. So here we see the execution cycles break down into busy cycles and the stall cycles. And busy cycles means that we can retire at least one instruction in this cycle, and stalled cycles are the ones where we cannot retire any instructions. So what we see is that basically more than half of the execution time goes to stalls when we execute typical transaction processing applications. Now, if you want to see like what happens in the stall time, where do these stalls come from, here on the graph on the right hand side basically breaks the stall time into where do these stalls come from in the memory hierarchy, and we are reporting them in a period of 1,000 instructions. And what is important to note here is that it's a bit misleading to draw these on top of each other, because some will be overlapped with others during actual execution. But it doesn't change our higher level conclusion here, which is that the L1 instruction misses plays a significant role for transactions. The footprint of a transaction is simply too big to fit in L1 caches, so you observe a lot of misses. So what can we do about the instructions of a transaction? And for that, we initially looked at what do these transactions actually execute, what are their instructions. And if we look at that, we actually see that on a multi-core system running concurrent transactions, no matter how different transactions are from each other, they execute a subset of operations from a predefined set. And these operations can be an index probe, index scan, updating, deleting, or inserting a record. So they are not so numerous. Now let's say we have an example control flow for a transaction. Here it first performs an index probe on table X, then updates a record there, then performs another index probe, this time on table Y. And based on a conditional variable, it can actually delete a record from another table, or insert a record to another table, and finally it deletes a record from Y. Now, let's also say that we have two threads executing this transaction, but with different input parameters. So T1 can basically execute it without taking the conditional branch, and T2 can execute it by taking the conditional branch and insert a record to table Z. So even the transactions of the same type, they do not execute exactly the same thing because of different input parameters or data state at that point. But the important thing is that they have quite a bit of code commonality among themselves, even though they are not exactly the same. So to quantify this commonality, we basically analyze the memory access traces from the standardized benchmarks again. And here I'm showing results for the TPCC only. So each of the pie charts here, they represent the instruction or the data footprint from either the TPCC transaction mix or the new order and payment transactions of TPCC. These two transactions are the most frequent transactions for TPCC mix. And each of the slices basically indicate the frequency of that portion of the footprint appearing in different instances in the transactions, either in the mix or specific transactions. So the dark red parts, for example, they are basically the instructions and data that we use in all the instances, whereas the light blue parts are used only in less than 30% of the instances. So what we basically see is that in the case of instructions, we observe a lot of overlaps across different instances of transactions, whereas for data, it's really low because we have 100 gigabytes of data set here. So at the database records level, you probably have, if you access data randomly, you have almost no commonality. So the few frequently overlap data is either the metadata information or the index roots in the database. So it's the instructions that we see a lot more overlap. And also we can say that in the same type of transactions we have more overlaps, which is natural because they have higher chances of executing the same database operations. Now, based on these results, what we want to do is basically exploit this commonality among transactions, different instances of a transaction. Now we again have two threads, T1 and T2. They are executing the same transaction with different inputs, and the different colorful parts represent the different parts of the code they are executing. And they are picked at a granularity that can fit in an L1 instruction cache. So in the conventional way of scheduling this will be probably assigned to one core, one of the idle cores in the system at that time. And as long as there is no I/O or context switching happening, they will finish their execution on that core. So for example, T1 is scheduled to the initial core here, and since it first needs to bring the instructions for the red code part, it needs to execute, so it will observe instruction misses for that part. And here I'm going to count such misses on the side. Now later when T2 comes in the system, again these two transactions or threads will observe instruction misses for the code parts they need to execute, and this will continue. Now, instead of doing this, we will do something like the following. So we will again schedule T1 to the one of the idle cores, and it will again miss the instructions it needs. But once it fills up its L1 instruction cache, we are going to migrate T1 to another core and instead schedule the newcomer T2 to this initial core. Now this time, even though T1 still observes instruction misses, T2 can reuse the instructions that is already in the cache. And again, once these two fill up their instruction caches, we will move T1 to another idle core and move T2 to the core that already has the instructions it needs. And this will continue. So by doing so, what we basically do is spread the execution of a transaction over multiple cores so that we can exploit the aggregate L1 instruction cache capacity for the instruction footprint of a transaction. And also we can localize instructions to caches so we can enable instruction reuse for the common instructions across transactions. Yeah.
So I'm sure this is a ridiculously stupid question, but why not just like let one of the cores be for everybody else, and then take some of them for these transactions that you know are going to be coming anyway, and load these instructions there to begin with, and just always direct people to those cores.
So, yeah, that's a good point, because actually I will present one other technique that sort of does that. I mean, initially you assign cores to specific parts of the transaction, and basically you migrate transactions based on that. So you prefetch the idea.
Does this model sort of presume that no other processes are running on the machine?
So for now, yes, but I think you can sort of give to the system the idea of like these are your cores. You cannot do more than this.
Plus, for a large-scale database, you would expect only the database to run.
Yeah. So that's also expected. But again, even if you don't have that, you can have some sort of idea of which cores are assigned to your application. So you can just do this over those. So this technique, we call it SLIC, which comes from self-assembly of L1 caches. And the thing is, it's a completely programmer transparent hardware level technique the way it is now. So it basically needs to track the recent cache misses of each transaction, and also needs to know what other caches have, so that we know when and where to migrate transactions. And this is done this needs to be tracked at runtime. So even though this is not maybe so costly, since we are doing already something already application specific, can we like exploit even more information from the software side, and not do this tracking basically at runtime. So for that, again, we will look at the instruction overlaps across transactions, but this time at a much, yeah.
Just one other. So how fast does your thread migration have to be?
So yeah, it needs to be like really efficient. So that in the with the traditional sense of context switching, this wouldn't be so efficient. That's why we implemented it like in a simulator at the hardware level, because if you try to do it over the operating system, basically this won't be so efficient, or you need really specialized libraries that would do fast context switching for transactions in particular.
Do you also switch the data when you switch the thread?
No, not right now, and actually that incurs some increase in the data misses, which I will show in the results. That's very good. Any more?
So if I have like a modern Intel machine, I can do a interprocessor interrupt a microsecond or so. Is that fast enough?
No, not for us. No, actually, I had at some point tried maybe setting core affinities at the software layer, because you have actual library functions to do that.
But actually, like, you send an interrupt to the other processor, right? So you basically transfer control to
Yeah.
the interrupt mechanism, not by any operating system.
Yeah, but I still, like, you need to, like, it tracks so many things during that process that, like, and some actually you don't need to track for what you want to do particularly, so you can do things much efficiently if you do more application specific techniques.
So here, the threads that you're migrating, are these processes or are they threads?
So they're basically hardware context with hardware threads. So not.
Your system, are they effectively like an OS kernel thread?
No, they are not OS threads.
So they're like a user level
No.
thread in one process?
So for us, okay, at the database level, you have the user level threads, and here, like, the technique actually uses that, like, the hardware level corresponds of this, so there are no OS threads. But of course, this was implemented in a simulator to sidestep that OS control, so with the current hardware and OS, you cannot exactly do that now. Okay. So here, to have more insights from the software side, we looked at this time the overlaps at a finer granularity. So we are basically looking at the instruction overlaps across different instances of database operations called within specific transactions. Again, payment and new order from TPCC here. So what we see is that, like, we had significant overlaps in the previous case as well, but here they are, like, they seem even more significant. So if we can develop some techniques that actually does the migration decisions from the previous technique based on the database operation boundaries or cache size chunks of the database operations, we can actually we achieve more precise scheduling decisions, and also don't need to track as many things at the hardware level. Now, next, I will describe a technique that does that, and we call it ADDICT, which comes from advanced instruction chasing. So ADDICT is formed of two parts: a profiling phase, and the phase 2 basically does the actual a workload run based on the migration decisions we gather in the profiling phase. So let's start with the initial phase. Again, we have the threads from before. Now in this phase, we run these or analyze their, again, memory access traces to find the database operation boundaries and internal migration points in these operations. So let's say for this particular transaction, it happens like it's shown here. So you initially mark the start point of the transaction itself. Then you enter to the index probe operation. You mark the entry point for that operation, and as you're executing index probe, when you realize that you fill up your L1 instruction cache, you mark that point as well and start a new phase for index probe. And this will be basically done for all the operations that might be called inside each transaction type in the system. Now, this part, of course, is a very simplistic sketch of it, but you do this with many transactions, and in the end, basically pick the most frequently occurring migration points. And this profiling phase, this can be either prior to the actual workload run, or you can incorporate it in the warm-up period for the workload run. And in fact, in our evaluation, we did our decisions based on 1,000 transaction traces, which was effective during the actual workload run. So it doesn't have to be too long, this phase. Now, during the actual workload run, the second phase, you basically initially assign each of these cores to each of the migration points you picked in the previous step. And what you do now is basically when a transaction comes, it starts at the start core. And when T1 here enters the index probe operation, it will basically migrate to the initial core for index probe. And then the newcomer T2 will be assigned to the start core. And when these two, again, when T2 enters the index probe and when T1 enters the second phase of index probe, this will be migrated to their corresponding cores, and this will continue. So this way, we again spread the execution of a transaction over multiple cores, exploit aggregate L1 cache capacity, and maximize instruction locality for transactions. But compared to the previous technique I described, basically you don't need to track as many things at the hardware level. So all you need to check is whether the current instruction you are executing is a migration point or not. And also you can achieve more precise scheduling decisions to further localize the instructions. Now let's see how these techniques perform in practice. Here, as I said, due to the limitations on the current systems, we do a hardware simulation here. And we are simulating 16 4-way out-of-order cores, and we have 8-way 32 kilobyte L1 caches. And we basically collected memory access traces from during the workload mix run on SureMT. We have them from 1,000 transactions in the mix. And specifically for the case of EDIC, we have another batch of 1,000 transactions to use in the profiling phase, so we don't run the same things in both phases. Now here, we see the L1 instruction misses in a period of 1,000 instructions for, again, the TPCC and TPCE benchmarks. The results are normalized to the conventional system, so conventional is 1 here. So both SLIC and EDIC, they can significantly reduce the L1 instruction misses. Of course, since EDIC know more about the software, it can be a lot more effective while doing this. Now, the downside of this technique is that, of course, when you migrate a transaction, you leave its data behind. So you have a penalty on the L1 data misses. But for L1 data misses at this level is not on the critical path for transaction execution. It's easier to overlap them with out-of-order execution compared to overlapping instructions. And as a side note, also, we don't really increase the long latency misses from the last level cache, so that's why this increase in data misses is not on the critical path. But now let's see how it actually affects the throughput of the system. So here we have on the y-axis the normalized throughput over the conventional system again, with the same setup. And what we see is basically we can, as a result of improving the instruction cache locality, we can improve the throughput with SLIC by 40% and with EDIC by 80%.
What was your assumption on the trade migration to get these results? Going back to Peter's question.
So in our simulator, we basically assigned the penalty for it.
And what was that? So it's like a constant number?
Yeah, it's a constant number. We had assigned a constant latency.
Tens of cycles or thousands of cycles?
I think it was tens. It wasn't so high. And yeah, it was like let's say less than 3% of the overall execution time. So it wasn't.
How frequently do they migrate? So for each transaction, it takes how many instructions and how many migrations happens within there?
So yeah, in terms of frequency, okay, I might have in the backup, but I know that EDIC migrates less than SLIC because it knows like where to go more precisely, but I don't have the exact numbers on the top of my head now. But I can check it and we can talk about that offline. I have it somewhere. So do you have any questions? Okay. To sum up what we have seen so far, we initially looked at how we can improve the scalability of a conventional transaction processing system. And for that, we basically eliminated the majority of the unbounded critical sections in the system using physiological partitioning. Now, within a core, we first looked at the sources of underutilization there, and we find out that L1 instruction misses is the significant cause. But we also observed that transactions actually share a lot of instructions, so we can improve instruction locality by making them share these instructions. And for that, we developed two alternative transaction scheduling mechanisms. One was programmer transparent and another one that was more software aware. And basically, both of these techniques were effective in terms of maximizing instruction locality and improving utilization in a core. But of course, being software aware reduces some of the drawbacks and improves things further. Now, let's see what is sort of a more higher level lessons that we can take from this work and what can we do, what expects us in the future. Now, at the beginning of the talk, I told you that like my goal during my PhD was to basically bridge the gap between what is given from the hardware side and what can transaction processing systems can actually exploit. But some of the lessons, at least I have learned during this work, I think are valid for software systems in general. So one is that I think we need to change the way we look at, we measure our scalability. So the performance numbers, looking at performance numbers is just not enough, because we have seen cases where we were scaling up perfectly on one generation of hardware, and with the next generation, things went rock bottom. So we cannot just look at our performance numbers when we show our scalability. And for us, I think the critical section analysis can be a good way to develop better metrics for when we look at scalability. At the other hand, I think with the emerging hardware, as we expect to have many more cores and as we have non-uniformity, heterogeneity, optimal scheduling of tasks will be the main challenge. And today here I show you two alternative scheduling techniques that aim to maximize instruction locality at the L1 level, because for instructions that's the important level for locality for us. But we also need to consider data locality with all the non-uniform access latencies we have on current hardware, and we have worked on that too. And in the case of data, I think the important locality level is to have things either in your local last level cache, or if your data is too big, at least in your local memory banks. So not to do any across socket minimizing the across socket communications. Now, after this step, from now on, what can we do is, from the hardware side, we would see basically a lot more proposals for specialized hardware. So we already have in our field proposals for building specialized hardware for specific database operations, both from academia and from some industrial labs. And even companies like Amazon or Google that used to opt for not specialized hardware and having commodity hardware, people from there start saying that when you have thousands of machines executing the same application, you better have the specialized hardware for it, because it's both more performance and cost effective. Now, for the software side, basically the software systems need to become more and more aware of the underlying topology, hardware topology, or hardware types. So this is not just for the heterogeneity, of course, but also to know where to put data, how to access the data for non-uniform, to minimize the effects of non-uniformity. And in the case of specialized hardware, basically we need to know where to schedule the specific tasks. And this is actually not just for a single machine, but when you have in the data centers, if you might have heterogeneity even across machines. So again, you need to know which tasks should run better on which cores, which sort of hardware primitives you can exploit for what type of task. We need to be more aware of that. And in that sense, maybe we can also get some help from the compiler community to basically dynamically generate some of the code that is specific for the specialized hardware type. So with that, I would say, building good and scalable systems, it is not the work of just one person. So these are all the wonderful people I had a chance to work with during my PhD years. And if you want, of course, you can now ask me further questions, but if you want to check later, I have a website that has a lot more detailed information about these projects. And also the storage manager we use, it's also online and available and well documented. So thank you.
Any questions?
Yeah.
So before sometimes we're about in that first section on the critical sections, that's where some commercial vendors have been going. What about the second part in terms of looking at moving things migration as a way to increase cache usage?
So in terms of commercial vendors, the things I've been hearing, they are mostly on the data analytics sites currently. So they try to improve special hardware, provide special hardware for like operations like scans and joins for mainly for big data applications. But again, at least when I was doing my internship at Oracle Lab, some of this work was also developed there. Like they are also interested in doing these such things for transactions, but I don't think there are really mature development in that area yet.
Thank you.
Mm-hmm.